All right, worksheet G, we're doing back-to-back events, compound events, and we get into the difference between dependent and independent. And independent events are when the occurrence of one event does not affect the probability of the other event. All right, excuse me. Find each probability, rolling a 1 and then another 1 when a number cube is rolled twice. So, first of all, these are independent because every roll of the dice um, is independent, meaning it has no impact on the next roll of the dice. Every time you roll the dice, your probability of getting a 1 is 1/6. And then the next time you roll the dice, you're wondering again, what's the probability of getting a 1? So it's 1/6 each time. It's unaffected by what happened the first time. When you multiply those, it's 1 in 36. And if you remember, we had a chart of this when we did the dice experiment. There's only one spot on the chart that's a 1 and a 1. 1 out of 36 spots. Number 3, the coin landing heads up 3 consecutive tosses. We're going to list the sample space, which we did in the notes, but we'll do it again here. You could have heads, 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 which is what we're looking for. But what else could you have? You could have heads, tails, heads. You could have heads, heads, tails. You could have heads. What am I missing? Tails, tails. I think those are all the options that start with an H. Then the rest of the options start with a T. You could have tails, tails, tails. You could have tails, tails, heads, tails, heads, tails, or tails, heads, heads. So there are 8 different outcomes in the sample space. You can look at that closer, but there is no other way. So what's the probability of getting 3 consecutive heads? Well, there's 8 total ways, and only one of them is all 3 heads. So my answer is going to be 1/8. Using the rule that we learned in class, if you want back-to-back-to-back events, you simply multiply the probability of all 3. And in this case, the probability each time is the same. Each time you toss that coin, it's a half. And 2 times 2 times 2 is an eighth. So it's the same either way. Now it says, show that these events are independent. Well, I just kind of did, I guess, is that the probability of A, and I'll say A, B, and C, because I guess I did 3 events in a row, equals the probability of A times the probability of B times the probability of C. Which I really just did, folks, because this here, this red part is right here. Those are my 3 events back to back to back, and I get 1/8. And then the probability of all 3 happening is this right here, which I just showed is 1/8. So I don't have to rewrite it, I don't think, but like, you know, this yellow side is 1/8, and the red side is also 1/8. So this shows that they're independent. When you see this saying, show me, you have to kind of convince me. So I would say, that this is 1/8. And on this side, I would write all of this out. Okay. I could do that. 1/2 cubed is another way to do it, which is 1/8. All right, number 4, rolling an even number and then rolling a 6. When a number cube, when a dice, this is just a dice, when a dice is rolled twice. Rolling dice are independent events because one roll has no impact on the next roll and the next roll and the next roll. So, so the probability of an even is the first event, And we're going to multiply that by the probability of a 6 for my second event. Okay, even number first, and then a 6. So the probability of an even event, even number, it's just 1, 2, 3, 4, 5, 6 on a dice or a number cube. Half of those are even, right? 2, 4, and 6. 3 out of 6, or 1/2. The probability of getting a 6 is just 1 out of 6. When you put it together, that will only happen 1/12 of the time. Number 5, a bag has 20 checkers, 10 red checkers, 10 black checkers. Determine if these events are independent or dependent, and then find the indicated probability. We're going to select 2 black checkers when they're chosen at random. And then here's the kicker, with replacement. So when I take a checker out, it goes back. Because it goes back, these are going to be independent events. Because my probability of, we'll say, checker number 1, and my probability of, we'll say, checker number 2, C1 and C2, they're the same. Because every time I draw, every draw has 20 checkers in the bag. And so that's a way you can explain independence. So the probability of getting a black checker first is 10 out of 20. And the probability of a black checker the next time is still 10 out of 20. That is really just 1/2 times 1/2. So that's 1/4. Very much like the coin toss in a way. Every time you draw in this situation, every draw is a 50-50 proposition. B. The only difference on B is that now you are not replacing it, which makes it dependent. So the probability of checker number 1 is still 10 out of 20. But now the probability of checker number 2 has changed because when I took out this first checker, I keep it. I don't put it back. So now instead of 10 black checkers, there's only 9 black checkers. And instead of 20 checkers total, there's 1 less. There's 19. So both the numerator and the denominator count down by 1. I like to write this just to kind of help myself understand the counting down nature of this. But now when I'm actually going to calculate this, I'd rather simplify this. So I would say that this is the same as 1/2 times 9 over 19. And then I can do it in my head. So it's 9 out of 38. If you want to change that to a decimal, be my guest. Be my guest. Be my guest. 6. Determine if they're independent or dependent. Oh, and then we're going to find the answer too. I should add that on here. Find the indicated probability. Okay. Okay. A coin comes up heads, and then a number cube, a dice, rolled at the same time. You're doing this at the same time, and it comes up 6. Does the coin have any influence on the dice? No. So this is independent. Okay. So the probability of heads is the first event. Even though they're happening at the same time, you can still think of it as one after the other. And then the probability of a 6. So the probability of getting a coin to land on heads is 1/2, and the probability of a 6 on the dice is 1/6. So that's 1/12. Which is really, look at that. Isn't that really the same question as that right there? All right. Letter B. A 4 is drawn from a deck of cards, set aside, and then an ace is drawn. So the key phrase is set aside, which means you don't put it back in the deck, which means it's going to influence the next draw. So the probability of a 4, and then the probability of I'll say the next 4, they're not the same. The first 4, the deck has 4 4s, and there's 52 cards. On the next draw, the number of 4s went down, and the number of overall cards also went down. So both of these count down because I did not put the card back, I set it aside. If you'd like, reducing can help. This is 1 out of 13. This is 3 out of 51. So it's going to be 3 over some big number. 500, 600, let's see. 13 times 51. There you have it, folks. 663. If you want to know how likely that is, well, let's divide it. D3 divided by 663. That doesn't happen very often. Oh man, I just read the whole question wrong. It's not it's an ace. Well, shoot. Well, what changes, folks? Well, we learn from mistakes, right? This doesn't change, but now the aces, there's not 3 aces because I drew a 4 out and I didn't put the 4 back. So that 3 changes to a 4. All right. So it's not going to change a whole lot. So now it's 4 is my numerator. 4 out of 663. Wow, that didn't really change very much. 0.6%. All right. Moving on. See, a 1 is rolled on a dice, and then a 4 is rolled on the same dice. How likely is that? Well, rolling dice is always independent. So what's the probability of a 1 on the first dice, and then you multiply by the probability of 4 the next time? These are going to be the same because they're just a single number on a dice, right? 1, 2, 3, 4, 5, 6 on a dice. The probability of a 1 is 1 out of 6. The probability of a 4 is also 1 out of 6. It doesn't matter that we already rolled a 1. So the answer is just 1 out of 36. 7. Event A and B are independent. The probability that both events occur is 42%. Okay. The probability that event A occurs is 0.70. Find the probability that event B occurs. I don't even know what these events are, but it doesn't matter. I know they're independent. And what do I know when events are independent? I know that the probability of A times the probability of B equals the probability of both of them happening, A and B. And they have given me some of this information. They have given me, let's see, both events, that's this. And they've also given me the probability event A occurs, that's right here. So put in what we know. So that is 0.70 times the probability of B equals 0.42. So it's really just an equation. What do I have to multiply? What does the probability of B need to be to make this work? I'm just going to divide by 0.70 on both sides, and I'll have it. So 0.42 divided by 0.70 is 0.60. So the probability that B happens or occurs is 0.60. All right, folks, that's all we wrote.